Hi, I'm a PhD student at the KIT in Karlsruhe with Linus Selinger and Sebastian Krumscheid. And I have the pleasure today to talk to you about my master thesis topic, which I did with Rob Scheiche and Dylan Nelson from Astrophysics. And so the goal of this thesis was to use an advanced uncertainty quantification method, which is called multi-level delayed acceptance, for parameter inference in cosmological simulations. So we've seen all kinds of numerical models today, but I think none were quite like these that you're going to see now. So I'm going to start by talking a bit about them. So cosmological simulations, like the ones I was looking at, they're really trying to, they're numerical models of the whole universe. So they model cosmological structure formation from really large scales down to the scale of galaxies. From the beginning to the universe, or from a matter distribution that resembles the beginning of the universe to nowadays. And they include cosmology, which is dark matter, cosmic expansion, and then also matter, which is discretized into particles of different types. And for these particles, then gravity is solved through a three-particle mesh scheme. And for all particles that interact hydrodynamical, so think about gas, the hydrodynamics is solved at every time step through a moving mesh finite volume method. So to produce objects that look like galaxies with this method, we need a few more things. And one of those is actually a minimum box size that is large enough, because galaxies actually don't form in isolation. They form in a realistic environment that is full of other galaxies. So the boxes that you need to run these simulations on are really large, and that actually introduces really, really large runtimes. And also, if you look at the picture on the right-hand side, it's made from a screen, or basically a snapshot from one of these simulations, and you can all these little dots are not stars, but they are whole galaxies of many stars. So this is supposed to show you how much matter actually needs to be in one of these boxes. But then on top of that, we actually also need more physics than just gravity and basic hydrodynamics, because physics on galaxy scales is also important, and that, but it needs to be modeled through some sort of subgrid models, because it can't really be self-consistent, or else we need to include way too many particles. And that actually introduces some partially stochastic elements to the solvers, because the processes modeled are also inherently stochastic. So think about small-scale processes that act on large scales through feedback. So if any of you have ever dealt with astrophysics, that like processes like supernovae would be something. So they're happening on the scale of stars, which is definitely below resolution of one of these simulations, but they inject a lot of energy into their surroundings, and that's actually that it has a large influence on the larger scales as well. So as you can maybe imagine, there are a lot of parameters involved in calibrating these subgrid models, but then also the cosmology. So all in all, there's something like 28 parameters that are relevant and in some sense physical. And the goal ideally would be to do some sort of model validation and do some inference on these parameters. And that is actually, so that is definitely not quite feasible with the methods that we have these days, but so the idea was to work toward that, and I'm going to introduce the setup that we finally used to do some inference on some parameters later, but I will first quickly go through Bayesian inference framework so that everybody is on the same page. So, and then I will also briefly introduce multi-level delayed acceptance for those who haven't seen it yet. So we think of our solver as some nonlinear measurable forward map that maps from a parameter space to a result space. And then the forward problem for that would be to compute the model output for some parameter. And even though the model is, the forward map is quite intractable, we can always use the solver and find this output, but it's quite expensive, is the problem. So the inverse problem would be to find for some observation the parameter that actually so that the model actually satisfies the observation. But the problem is with observations and also with these partially stochastic models is that there's that they're just never going to quite satisfy observations. So we need some sort of error or noise term to satisfy the statistic relation. And we can make for now the assumption that this noise is Gaussian with some covariance matrix. But yeah, so we're in the Bayesian setting, so we recognize that actually finding one parameter that satisfies the observation is not a good treatment of the task. It's rather that we want the probability distribution on the parameter space that tells us a lot about how our model relates to the data. So with Bayes' theorem, we have a formulation for this posterior distribution on the parameter space that depends on some likelihood and some prior distributions of the parameters, and then also some normalization constant. And the assumption about the statistics with the Gaussian noise tells us that the likelihood should be of this Gaussian form that's stated here below. Yeah, and I think the next step then is to sample from the posterior, which we can do because we can evaluate the likelihood. So the algorithm or the naive algorithm to use for that would be Metropolis Hastings. I'm sure many of you have heard of that. Oh, sorry, yeah. So Metropolis Hastings algorithm constructs a Markov chain that has the target distribution, which is the posterior, as a limiting invariant distribution. And the generating algorithm is quite simple. So at some point of the parameter space, we make a proposal in every step. And then for this next point that was proposed, we calculate the acceptance probability, which depends on the relative likelihoods of the points. And it's a very simple idea. And it produces a set of points in the end that in its distribution approximates the posterior. And for some fictitious underlying distribution, you can think of this algorithm as producing something that looks like this. So it walks around, it walks to the place with high probability, but then also goes back a bit because we never quite, so it is always possible also to go up to a place with lower probability, even though the acceptance probability is then quite low. So this algorithm is very nice, but the problem is it is just not efficient enough. Because for every step of the algorithm, we need to evaluate our forward model, and that is just very expensive. And then also for the best exploration of the parameter space, we actually need that there is a certain rate of rejections as well. So many of the evaluations of the expensive forward models don't even go toward our goal of obtaining samples from the posterior. So there's this idea, it was introduced in 2005 by Kristen and Fox. It's called delayed acceptance, and it introduces to Metropolis Hastings a step where on a coarse model or a coarse approximation to the model, we check our proposal and see whether it could be a good fit. And if so, we promote it to the finer chain and then check the full model. And we hope that this step of pre-checking actually makes the acceptance probability higher on the fine chain. And this basic idea, it relies on the fact that we have a coarse distribution, which coarse target distribution, which relates to a coarse forward map. So we need some sort of approximation, but if we have that and the approximation is somewhat good, then the resulting fine chain still fulfills the Markov property and approximates the posterior that is induced by the fine forward model. So that means we can improve proposals by taking steps on the coarse approximation, and the samples, because we modify the proposal, the samples on the fine chains should also be less correlated. Yeah, I realize this is a very short introduction, but maybe if you're interested in the method, we can definitely talk after. So I want to continue by talking more about how I use this method in my setup. So we have this large simulation from astrophysics, and it has many parameters, but we decided to only look at a subset of this parameter space, which is outlined here. It's just 3 parameters. Some are physical, some are rather tuning parameters. No, actually, they're all rather tuning parameters with at least the physical equivalent is a bit difficult. So you couldn't go to the universe, like look at observations and constrain these parameters. So for a Bayesian setup, we look at some model outputs for which there are actually physical equivalents, so measurements. And from that, we can compute the likelihood and form the algorithm on the parameter space. And all of this is done through UMBridge, or Umbridge is, yeah. In a very nice setup on a high performance computing system. And the sampling actually is done with tiny DA on the parameter space. And my idea was to now talk a bit more about the nitty-gritty details of the uncertainty quantification in these models. So I said already, we have these models, and we can make them coarser or finer by changing up the mass discretization. But we can only do that to a certain point. So if we make the discretization too coarse, the representation of the universe is not good enough anymore. And if the volume is chosen too small, then it's also not a good approximation anymore for what a large model would do. So we can define some sort of levels via mass discretization, and I've visualized that here. These are two different levels. The one on the top is actually the coarser one, and the one on the bottom has more mass discretization particles. And you can also see that directly in the difference of the runtime. So I tried to make that plausible by including some CPU hours, although this is a very imperfect characterization, because actually the runtime also really depends on the parameters, which is not great in the context of parameter estimation and Markov chain Monte Carlo. But yeah, this coarse model needs some 32 CPU hours. And the next finer model already needs 512 CPU hours. And eventually, of course, we would like to look at models that actually take way more CPU hours. Yeah, so this was the setup that I looked at mainly so far. And we have the problem also in the with regard to uncertainty quantification, that the solver is partially stochastic. So there is some noise in the model outputs, and that together with the very long runtimes led us to the conclusion that we actually should use some sort of surrogate modeling as for a very fast coarse approximation, and that's what we did. So here on the left, sorry. So here on the left side, you see visualized the simulation output that we condition on. So there are some measurements. This is actually called the galaxy stellar mass function. And there are some measurements in gray. There are simulation outputs at different resolution. So these are instances of the illustrious TNG model. The gray and black lines are very high resolution models, actually. And the blue one is the coarsest model that I was able to run with, or the one that takes 32 CPU hours. So what we did is we used Gaussian process regression on some 600 model evaluations that were chose by Latin hypercube sampling. And from that, I constructed a Gaussian process surrogate, which you can see visualized on the right side. And from that, you get a really fast surrogate model that models the behavior with parameter variation. And as you can see, it does quite well when it's compared with actual model evaluations. So the actual model evaluations are blue. And what you can see is that it basically even smooths out some of the noise. So, and we can then use the surrogate and the different levels that as well that we could define of the simulation to use multi-level delayed acceptance. And I've done, so the results are quite preliminary because also being the ability to obtain results was really hinging on the HPC system and the Umbridge setup. And since I was able to obtain these results, both of these things have improved quite a bit. So these are quite old results, but they were a first test. And in this first test, I was sampling on the simulation level and comparing Metropolis Hastings to delayed acceptance with the surrogate. And one setup also used adaptive error modeling, the other didn't. And what you can really see is that the acceptance rate overall, so the number of samples was really increased dramatically by the use of the surrogate and delayed acceptance. It's not quite clear from these results what the adaptive error modeling does, but it's actually quite promising. So on the right-hand side, you see something that we eventually would want to have. So this is corner plot is just obtained from sampling on the surrogate. So it's a single level method, just Metropolis Hastings. And there we are able to draw quite a lot of samples because it's very fast. And then we can see some marginal distributions, and it points us into the direction of what we can expect to see. So yeah, mainly maybe one comment on what we can see is actually that the chains want to leave the parameter space that we specified. So I haven't talked about the priors that we chose yet, but because there's actually not a lot to go on, we chose the priors as flat around a certain range of the parameters that the astrophysicists normally use. But actually with fixing the parameters in this way, the simulation instance that we used can't really satisfy the observations well. That's why the chain wants to leave the parameter space. But the next step would really be to repeat the sampling, not only with the surrogate, but with the actual model, and also include higher resolution models. So moving from delayed acceptance to multi-level delayed acceptance. And yeah, eventually being able to say something regarding how well these models are parameterized, or so it's not entirely clear what the finding would be, but I imagine that a cool finding of this work would be, okay, the astrophysicists normally use it with this set of parameters, but actually there's another area of the parameter space that is also quite likely. So I have some take-home messages. So the first one is multi-level delayed acceptance or delayed acceptance sampling as a variation of Metropolis Hastings is a quite powerful tool, especially when it's combined with surrogate modeling. And it also works for very intractable forward models that don't make a lot of sense mathematically. And then also regarding Umbridge, my message is that, yeah, I use it on an HPC setup on the Helix cluster with Slurm, and it runs very smoothly, even though the specific requirements of the code pose somewhat of a struggle. And yeah, maybe this, you can connect this to your own work, or you see this and you think, oh, this is nice. How did she manage to do that? And if you think that, just let me know, and then we can have a chat. Yeah, and I'm happy to take questions.